All right, so today we are diving into just a brilliant paper. It's titled Network Theory Classification of Quantum Matter Based on Wave Function Snapshots by Andreoni, Vitale, and their collaborators.
The core insight here is, well, it's that you can classify the fundamental phases of quantum matter, gapped, gapeless, even the topological ones, without needing to know the Hamiltonian that actually created the state.
Right.
They do it purely by looking at these limited, noisy snapshots that we can actually get from quantum simulators.
So you're saying you can figure out what a phase of matter is without using the traditional physics playbook of symmetries or order parameters. They're basically turning quantum data into a network to see the physics.
That's it, exactly. And the whole framework, it really just rests on two big steps. Step one is about filtering. It's using algorithmic complexity, applying Occam's razor, really, to find the minimal complexity measurement basis. They call it alpha min.
Okay, and they use a metric for that.
Mm-hmm.
The intrinsic dimension, ID dollars.
Yep, the intrinsic dimension. And then step two is building a wave function network from those filtered samples and classifying the state based on that network's structure. Specifically, its degree distribution P et al.
And the results for one-dimensional systems are pretty stunning.
They really are. The four standard quantum phases, paramagnetic, critical, spontaneous symmetry-broken, and symmetry-protected topological. Each one maps to a unique fingerprint. A specific combination of high or low eindelars and one of three network types, structured, scale-free, or Erdős-Rényi.
So that's the mission then, a totally agnostic, data-driven way to classify the quantum world.
Exactly.
Okay, let's unpack the problem they're actually solving here. I mean, for centuries, right, classifying matter meant you knew the equations, you had phase diagrams, you knew the symmetries, the observables.
But that's a luxury you have with classical systems, isn't it?
Totally.
With synthetic quantum matter.
Right.
I mean, you're working with trapped ions, circuit QED. You just don't get the full wave function. It's way, way too big for, 50 spins? The Hilbert space is $250.
An astronomical number, and instead we get just a few thousand of what they call stochastic snapshots.
Right, these collective projective measurements. Mm-hmm. You're in this crazy regime where the space is exponentially large, but your data is just this negligible little sample.
No telltales, that's the challenge.
That is the crux of it.
Yeah.
How do you possibly connect that huge, random-looking, basis-dependent data to the actual physics of the system in a way that, a human can actually interpret?
And the paper makes it clear the first step is critical. It's basis selection. That choice can either reveal the physics or hide it completely.
Yeah, think about a simple ferromagnet, right? All the spins are lined up. If you measured along that z-axis, the direction of alignment, your snapshots look ordered, predictable.
Makes sense.
But if you measure that exact same state along the x-basis perpendicular to it, your snapshots look completely random. Pure noise. The order is totally masked.
So the goal is to find the one basis, the one angle of observation that makes the data look as simple and compressible as possible.
Exactly. That's where the minimal complexity basis, the alpha min, comes in. And they use the intrinsic dimension, ED dollar, of the data as their proxy for complexity. So they test a few bases, X, Y, Z, just pick the one with the smallest dollars.
The Occam's razor idea. Can you give us an analogy for IDETA? It sounds a bit abstract.
Sure. Imagine you have a crumpled piece of paper floating in 3D space. You could use three coordinates, X, Y, and Z, to describe every single point on it. Very complicated.
Okay.
But if you just uncrumple the paper, you realize all those points actually live on a simple 2D sheet. The intrinsic dimension of that paper is 2, even though it's embedded in 3D. So ideal is just the minimum number of variables you need to describe your data.
I see. So if the quantum state is highly structured, like all spins align, the data snapshots are really redundant. You don't need much information to describe them, so you get a low ID brawl.
Precisely. And if the state is, super entangled or fractal, the ideal will be high. Low ID dualism means high compressibility, which points to structured physics.
And they calculate this with something called the TWO-N method.
Right, which is a key practical detail. It's a robust estimator based on nearest neighbor distances in the data, and it works even when your sample size is pretty small.
Okay, so once we've filtered the noise and found our minimal complexity basis, alpha min, we move to step 2.
Step 2, network construction.
Yeah.
The snapshots you collected in that minimal basis now become the nodes of your wave function network, or WFN.
And we need to draw lines, connections between these nodes. How do we define how similar two quantum measurements are?
They use a really elegant idea from spin glass theory called the Parisi 2 replica overlap. But for the spin 12 systems they're studying, this complex thing simplifies down to something very intuitive.
The Hamming distance.
The Hamming distance.
Oh, so it's literally just you line up two snapshots, two strings of +1s and -1s, and count how many spins are flipped differently between them.
That's it. It's that simple, which is what's so powerful about it. It's physically intuitive. You draw a link between any two snapshots. If their Hamming distance is below some cutoff radius, $3.
And suddenly your quantum classification problem is a geometry problem on a network.
You got it.
And this is where the second half of the fingerprint comes in, the network structure itself. The paper identifies three main types of WFNs that emerge.
Right. The simplest are the Erdős-Rényi networks. These are basically what you get from pure randomness. They have a Poissonian degree distribution, meaning every node has more or less the same number of connections.
Then you've got the ones everyone's heard of, scale-free networks.
Exactly. Like social networks or the internet. Their degree distribution, PK, follows a power law.
That power law is the key, isn't it? It means there's no preferred scale. You get these massive, super-connected hub nodes and then a ton of nodes with just a few connections.
And in this quantum context, those hubs are the snapshots that are really similar to a whole bunch of other very different configurations.
And the third type, the probability networks.
These are highly structured. They can look a bit Poissonian for nodes with few connections, but they have these huge peaks at high connectivity.
What do those peaks mean physically?
They mean you're deep inside a stable phase. If the system is gapped, the quantum state is stable, and so your sampling process keeps hitting the same few typical configurations over and over again.
Ah, so those typical states become the big hubs, the peaks in the network.
Exactly. And what's amazing is that this whole framework works with just a few thousand samples. It's efficient, and because it uses things like Hamming distance, it's not some black box. The results are physically interpretable.
Okay, let's put it all together. Let's look at the actual classification of the 4 1D phases. This is where the pairing of complexity and network type really shines.
Starting with the simplest case, paramagnetic phases. These are gapped, pretty simple product states. In their minimal basis, they have a small Iman day, they're very compressible, and they produce a probability network.
Which makes sense. The energy gap suppresses weird quantum fluctuations, so the samples all look like one or two simple classical-like states.
Exactly. Now for the gapless systems, critical points or phases. We know these things are all about scale and variance, right?
Right. Correlations that decay algebraically.
And the complexity reflects that. Critical phases show a large Iman day. They're incompressible, and they give you that scale-free network structure. The network itself is literally reflecting the physics, the lack of a preferred length scale.
It's like the fractal nature of the physics gets imprinted directly onto the network of samples.
That's a great way to put it. Then we have the ordered states, spontaneous symmetry-broken phases, let's say with a simple local order, KN1 $1.
Okay.
Now, in their minimal basis, these also show a very low Iman beta and a probability network, just like the paramagnetic phases.
Wait, so that raises a big question. If the metrics look the same, how does an experimentalist tell the difference between a simple paramagnet and a state that's, spontaneously broken some symmetry?
Good question. What does the network structure show that distinguishes them?
Yeah.
The key is degeneracy.
Yeah.
An SSB phase, because it's breaking a symmetry, has to have multiple degenerate ground states,
right?
Like all spins up or all spins down. So when you sample it, the probability network doesn't just form one big clump. It fragments into these distinct, isolated clusters in your data space. Each cluster is one of the degenerate ground states. That clustering is the dead giveaway for SSB.
That's the physical signature. Brilliant.
Now for the trickiest one, symmetry-protected topological phases, SPTs. These have no local order parameter at all. The entanglement is non-local.
So if there's no local order, any local measurement is just going to look random.
That's exactly it.
Oh.
And they are diagnosed by this combination of high grounds across all measurement bases, because no local view can capture the non-local order, and an Erdős-Rényi network structure. The samples look basically uncorrelated and random.
Okay, but that brings us to another challenge. What if you have an SSB phase, but its order parameter is really complicated and non-local, spanning many sites, so K10011? Locally, that might also look random.
It would.
So how do you tell a complex SSB from a true SPT phase? They might both start with a high IDI.
Right, that's a fantastic question. They tackle this with a really clever procedure from condensed matter theory, the Kadanoff type decimation scheme.
Which is basically a coarse graining method.
It is. It's a rigorous coarse screening. Yeah. You do this parity blocking over bigger and bigger chunks of the system, $2 out. It's like you're slowly zooming out from the fine-grained data and tracking how the complexity, ADID, changes as you zoom.
That is clever. So what happens?
For an SSB phase, with that complex k-dollar order, the complexity IDAR starts out high. It looks random. But then it will abruptly drop once your coarse graining scale, $2, gets big enough to match the size of the hidden order parameter, $2.
At that point, the hidden order is revealed and the state suddenly becomes compressible.
Exactly. And it'll flip over to a probability network structure at that new scale.
But hold on, if your data is so sparse, just a few thousand samples, isn't there a huge risk that this decimation process just loses the signal in the noise before you find anything? How robust can it be?
That's a fair point. But that's where the robustness of the TWRNN method for estimating dye really helps. It's pretty good, even with sparse data. And they showed this numerically. In the Suschreiber-Heeger model, the SSH model,
Which has an order with supports, Siver2R?
right, they showed the complexity drop sharply right after the first decimation step at 8 through hour 1, which corresponds to support 2. It worked just like the theory predicted. But for the SPT phase, the complexity stays large and independent of the decimation. It's incompressible at every scale.
So the theoretical predictions are solid. What about the simulations on standard models?
They backed it all up with matrix product state simulations. The Ising model was a perfect match. Low ID in the gap phases, high ID in right at the critical point A till 1.
And the XXE model?
Same story.
Yeah.
Low ID in the ordered phases, high ID in the critical phase.
Mm.
And the clusterizing model, which is known to host an SPT phase, confirmed that pervasive high ID and the URN structure in the topological region.
The finding about the critical point seems really significant.
Oh, it was. At the Ising transition, the WFNs were definitively fat-tailed, compatible with a power law. This was really solid numerical evidence that criticality, when viewed through this lens, is the emergence of a scale-free network.
And they didn't just eyeball it. They used finite size scaling analysis, which is the gold standard in studying critical phenomena.
Right. And they showed the power law exponent, gamma, was stable and didn't depend on the system size. That's how you know it's a real universal property and not just some simulation artifact.
That's the kind of rigor that makes this feel like a fundamental statement about physics, not just a data science trick.
Totally. So if you look back, the two most surprising insights here are probably one,
The diagnosis for topological phases.
right. It tells you that topological correlations are this weird combination of being incompressible at any scale you look, while also having a network structure that looks completely random, like an Erdős-Rényi network.
It's the quantifiable signature of non-local order.
Exactly. And the second big insight is confirming that critical points are fundamentally described by scale-free networks. It's not just that some correlations are scale-free. The entire geometric structure of the wave function samples is scale-free.
So what's the big takeaway for someone running a quantum simulation lab today? This seems to provide a really robust, interpretable way to classify matter without needing to know anything about the system's symmetries or whether it's gapped or not.
I think so. It puts all these phases, PM, CFT, SSB, SBT, on the same footing. And if you think about the bigger picture, this deep link between the algorithmic complexity of a state and its physical behavior, that could change how we do diagnostics in quantum computing. We could start focusing on the compressibility of a state, not just expectation values.
And methodologically, they suggest you could push this even further with more advanced network science tools like persistent homology to get an even finer-grained classification.
For sure. That'll be essential for tackling harder problems, like gauge theories in more than one dimension. And conceptually, you can just pick this up and apply it right now to study things like out-of-equilibrium dynamics, deep thermalization, where information spread is everything.
Or even to characterize these new, powerful variational wave functions like neural quantum states, where it's not always clear why a certain basis makes a state easy or hard to sample.
Absolutely.
It really makes you wonder. We know that states like SPTs are computationally harder to prepare on a quantum computer. They require more complex circuits. And this work shows they also have high algorithmic complexity in their sampling distributions.
While simple paramagnets are easy to prepare and are highly compressible.
Exactly. It suggests there might be this profound fundamental relationship between the circuit complexity needed to build a quantum state and the structural simplicity of the probability distribution you get out at the end. And if that correlation holds up, that could be an incredibly powerful new guide for designing the quantum computers of the future.